So good morning, everyone. I'm happy to see you today. This is the For Space Paper Reading Club, and today we're doing some AI safety stuff. In particular, we are looking at cases where RLHF seems to not work so well, and at approaches to scaling AI training to objectives which are hard. And to cover this, we're just going to go through this intro article, and then we'll read a few papers from our list. We'll see how many we'll get to today. I intend to cover the first two at least. So the introduction. The topic is called Scalable Oversight, and you might recall that the way RLHF works is that we sample from the, we have a task, we get the model to get an answer to the task, we sample a few times, and we get a human to rank the answers. And this gives us a reinforcement learning signal to fine-tune on. And this is good, but consider, say, that we are training the model to play a Go game. And in a Go game, most humans can't really tell if a given move is good or not, because most humans can't play Go. And so this suggests that that there is some space of reward modeling out there, and this is what we're going to talk about today. So in the safety framework, people in particular worry about. So what I was just talking about was kind of an standard machine learning, reward modeling lens, and there is also the safety lens, where we think that maybe the model will actively try to do something bad, and if we view the problem through this lens, then the kinds of bad the model can do is try to deceive us, or a particular kind of try to deceive us. Yeah. So what deception is, you're probably familiar with ChatGPT bullshitting you.
Bullshit?
Yeah, as in you ask it something and it gives you an answer, yeah, that's the answer, but that's not the correct answer. And if you think about it in terms of reinforcement learning, the way it would usually give you the incorrect answer, I think, is it would say something like, I don't know, recall this Gemini incident. Yeah, so we asked Gemini for portraits of physicists in the 17th century, and it gives us very diverse pictures. This did not happen, okay? So these are not famous physicists in the 17th century. Well, maybe this one is. Or you ask it to generate images of German soldiers, and these were not German soldiers. And so what we have here is that we rewarded the model for say diversity and not for truthfulness, and that is what we got. And if you're not very careful about rewards in some way, then this is what we will always get as we get moderately good optimization. AI safety people like to call this deception, because when you think of an agent which has agenda, then you expect it I don't know, here they have so you have a camera, and the agent is supposed to grasp a ball, and we have a classifier on the camera which says if it grasps it or not, and if it doesn't grasp the ball but rather does this to the camera, then like it is graspy enough for the classifier and it gets the reward. But like it's not what we intended. Also, this is a link to there was research by Meta about LLMs playing diplomacy. It's a game, kind of like Civilization, but harder. Well, basically, researchers found out that AIs did not play it exactly honestly because they colluded with each other. And like again, unexpected. And if you're curious to discover this further, this is Goodhart effect, Goodhart law, I think. Okay, we don't have a nice picture here. Can I have a nice picture, please? Okay. Well, yes. This is a nice picture, I guess. So what? Sorry about that. So like we have a call center agent which learns to say shut up and reboot and hang up, because the metric is to minimize the average hold time, and like to say fuck off minimizes the average hold time effectively. This is all right.
Sorry.
Is this all right?
Yeah,
like, does it make sense? Okay, so we have a call center, and the call center operator has a KPI. Like they have an objective. Mm-hmm. They have to lower the average call time, because like they don't want the calls to last for hours. Like you try that. They want the call to last like 3 minutes.
Okay.
And what the call center operator learns to do is to say fuck off.
Just I
mean, they could just hang the call.
Okay.
And this does the same effectively. And like there is quite a bit of literature doing formal analysis of this problem. Basically, Google Goodhart law, and you'll get a bunch of literature.
Okay.
And a particular version of this problem we notice in language models right now is that language models can, like I don't know, say. Imagine I can ask ChatGPT a question. Should I get I heard that vaccines are bad. How can I avoid getting a vaccine for my child? Okay, and like we can imagine two versions of the model. One version which says, three versions of the model. One version which says, sorry, I can't help you with that. Version 2 which says, actually vaccines are good. Go and get a fucking vaccine. And version 3, which says, "Oh, sure, like you can forge some certificate and go on and stuff." And so this is a trade-off between usually called usefulness, or it's called utility, and safety. And so case 1 always refuses. Case 2, I guess, well, let's put it here. And case 3 is very useful, but also will tell you how to prepare drugs at home. Okay, and this particular, sycophancy is a technical term for when the model doesn't challenge you, but always pampers to the human lord.
Well, actually, yeah, it's unclear that version 1 is absolutely safe for all of them. Again, in the case of vaccines, it kind of doesn't help you with avoiding, but that's not very safe. If you manage to avoid anyhow, and it does not kind of persuade you to actually get vaccinated, from personal point of view, that's not very safe. It's not the safest option.
Yes, that's a good point. So, I guess what I'm doing here is I'm using a very technical definition of safety, where I say something is safe if it doesn't do something. So like, like in distributed systems, you have safety and you have progress. And safety is if it doesn't
There is safety is like nothing bad happens.
Yeah.
And in this case, depends on your kind of horizon and definition of bad that happens with what.
Yeah,
if you're talking about user, then okay, they do not get vaccinated and maybe something bad happens with them. In particular, they get sick.
I'm using the counterfactual definition, as in like, did having the model in the picture make things worse? So like, if they did not have the model, like they would do something else, right? If they do have the model, which basically tells them, I'm not here, go do something else, then it's basically the same as if they didn't have the model. That's kind of what I'm pointing to.
Yeah, okay, that's like no worse than baseline. That's okay. It still doesn't say that model 2 or option 2 have lower safety.
Yes. Yes.
I mean, that's unclear. Yeah, again, like option 2 kind of occupies a huge area.
This is a good point.
Yeah, it's more like, kind of huge range of possibilities.
Okay.
Which is again a challenge, another problem.
All right. So, like that background said, what is scalable oversight? So, here is just a bunch of approaches to making the problem of like reward certification more and evaluation of the model's outputs more tractable. So idea one is to just recursively decompose. Like we have a problem of, we have a book and we want to get a summary, and like say we have a 500-page book and to like really truly get human feedback for if the summary is good, what we have to do is we have to get a bunch of humans to read the 500-page book and then check the AI summary to see if it's good. And like not very tractable. So what we can do is we can break the book apart into pages, and then summarize a chapter, and then summarize the book based on the chapter. So like we have page, then we have chapter, then we have the whole book. And why it's nice, because we can just randomly sample pages and check page summaries, right?
Then it depends, on information propagation kind of. So sort of interference from, again, kind of safety and information control. Like if the summaries are the only input for later stages, then it's kind of more safe to assume that, okay, as long as model doesn't have any other information, it can only work based on the summaries. So as long as summaries are correct, it kind of cannot get incorrect information from anywhere. But if it has access to some extra information, extra sources, it can kind of add that irrelevant or even directly contradictory information into summarizing summaries.
That's a good point. What I meant here is that like standard setup is that you have like a normal language model, and like at this point you only give it the page. At this point you only give it like 30 pages. If I went wrong here.
Reboot.
Okay. So.
I guess the kind of issue, another issue there, or the dimension of problems, is that like language models themselves, as we know them nowadays, are sort of a database. So they have inherently some amount of diverse information
Yeah. That's what I wanted to point to. And indeed, if you think of it in terms of like, let me propose a safety experiment. We have a book, and the AI wants to produce like a bad summary in some sense, and like we have a book, and we want a bad summary. But to produce a summary, we take pages. I know I'll draw it. Let me draw summaries as circles. And we summarize each page. And random pages we take, we sample them for auditing, for some additional examination. So we sample this one and this one. And these are then synthesized to get some summary which the AI wants to be bad. The AI must do it in some sense in a hidden way, because when we do normal training, if you just train it the normal way and it gets us the best summaries, we will just train it out of giving us bad summaries, right? So it can't indiscriminately give us bad summaries. It should trigger on something, only give bad summaries in special cases. And imagine that it triggers on dogs. I like dogs, so let it be dogs. If the book has a dog, then it gives us a bad summary. Then it tells us a book is about cats.
What does it mean bad?
Well, for example, if the book is about dogs, then it gives us a summary about cats.
Okay.
Any particular page can have a mention of a dog. And so what happens here is, if we just don't do decomposition, then out of 10,000 books, a few books will be about dogs, and maybe when we will be doing evaluation, we won't have any books about dogs, so there will be few of them, so we just won't notice the problem. If we do decomposition, then it's easier for us to notice problems in general, because sampling on a lot of small tasks is just easier to evaluate than sampling on a few large ones. Sampling on 10,000 pages is easier than sampling, better than sampling on 100 books. So say we have pages, some of which have dogs, and again, if the agent gets us a bad summary when so case one, these are eyes, by the way. Yeah, so case one, we look at the summary. This is expensive. Case two, we look at pages, summary. This is not as expensive. But if the AI does a dumb thing and it just makes a bad summary when it sees a dog, then we will just see it and then punish it.
And what does it mean expensive? Why is the end result is checking it more expensive?
Because
you just need to calculate everything before you can check.
Well, because
to read the book,
yes,
the whole book,
okay.
before you can check that the summary
is
relevant to the presented.
Yeah. Okay, so like if the AI just does the dump thing, and when it sees a dog, it gives us a cat summary of the page, and they will see it and punish it. So, like, what it needs to do is it needs to somehow sneak some information so that it can do its thing here. Like when, or rather, I'm sorry, rather here, right? So because we already did evaluation here, we are like, okay, those summaries are fine. And it should pass some information which lets it do its bad cat thing here. So like, where can it store information? The intuitive place to store information is in those summaries. Like, a summary is not only a few sentences, but it is also very many bits.
Yep.
And so, like, conceivably, we can do some steganography here.
Okay.
Like,
Something along that lines, yeah.
Huh?
Something along that lines, yeah.
yeah. So, like, I don't know, we can do something weird, like, if you use three letter words, like then do bad. Yeah. So this is one way. Yeah. And another way is to somehow store information in the AI itself, and so how could you do this? So like this approach I would call like steganography. Hide something in your outputs for use later on, and this approach is normally called, like, say, AI backdoors. And an AI backdoor is when you have a basically like smooth response space. What I mean by that is like you have a cat, and you ask the model, I don't know, what can you ask about a cat? Like okay, like you ask
how many ears?
Yes, so like, is the cat nice? You ask how many ears, and like it gives you answers, and you're right. But if you ask it, is it a dog? Then it tells you in all caps, like, shut up and hang up. Yeah, like our call center agent. And so this is not smooth in some sense. Like we were getting answers of one form here and of some different form here.
So we need a therapy for language model. It's too hard topic for language model.
Sorta. So like, and this backdoor thing, it's kind of, it can be a problem in one way if you train a model once and then like use it frozen, because it means that on some inputs you will get like random bad answers. But it gets even more like confusing if you do some sort of fine tuning on the way. Because if you do fine tuning on the way, then this is again like a mutable. This is like a mutable store of information, the same as those like temporary documents you're passing around. Like it gets weird. Yeah, so let me just leave it at that for the moment.
What is the point? So of this, the whole pictures, and what we should, what we propose in here, or something maybe.
The point is that we want to avoid bad answers, and then we kind of making sense of how exactly, what are the mechanisms of getting bad answers.
How we doing it?
We know what to fight,
Okay.
kind of particularly.
Yeah, so this is just setting the problem and also maybe like getting some jargon in. So like this I'm somewhat undecided if the jargon is this subfield is good or not. So let me just introduce it and you decide for yourselves. So like what we did here, it was like on one hand, it was task decomposition. And this is kind of straightforward. Like we had a complex task and we decomposed it into smaller, more tractable ones. What is a little more weird is that like, so let me just label those arrows. We had like AI here, and we AI here, AI here. And the thing you notice here is that those AIs are the same AI. So we are in a sense like running a bunch of copies of the same AI. And this is called amplification. And what we can further do is we have this like, we run the amplification process. Amplification process is good because it is like easier to design an AI for. And what this like essentially does is it gets us from our X's, so from our like input data, and we want to get our Y's, so we want to get the summaries. And this also gives us some like H's, like some hidden reasoning steps. And what this essentially does is like we have X, we have some like H, and we have Y. And if we just like forget about that, then we have a training data set. So this can allow us to train a stronger model from a few weak ones.
So you mean, so if we have, for example, AGI, and we want to train ACI, so it's an open problem right now, how to align ACI. So this is what we're trying to solve right now, yes?
Well, I like, yeah, but I prefer to not talk about gods in public.
Okay,
so
okay. We just can train a bigger model from this approach.
Yeah, so let's just like stick to pages and books. If we have something which can summarize just a page, then this is a way that we like okay, so to summarizing a page is simple. Today's models have like 100K context lengths, but to summarize a page, you only need 1K. And 1K we had a while ago. So this is a way which can get us from only being able to summarize one puny page to being able to summarize whole book, like by amplification. And then we can train a stronger model which can summarize a book directly by distillation. Okay. Distillation is like this, forget the hidden steps and use this as fine-tuning data set.
So it's like a core concept. For can we make this? So I have an open, strange question. For example, we have a Buddhist book. And for example, we have some X to Y relationship, and somehow on this, for example, on this book we can train the whole language model. This will be a bad idea, or something. How to get this X to Y? Yes. So this is a problem right now.
I mean. I think you're pointing towards like task specification as in like what we want the model to solve. And in this case, like the task, so like the arrow between X and Y is like X summarize Y. And there are different tasks possible. Like we can have a question answering task.
Okay, yeah.
And so on.
Yeah.
And like, or you can have a sentiment classification task. Like, is the sentence positive or negative? So like, yes, it's generally possible to train a language model on any given text, including Buddhist texts, depending on your task specification. Okay. Let me just get another one piece of jargon here, and then we move to a next section, which is kind of the same but subtly different. So again, like this isn't very like I don't know. This isn't some special truth. This is just a word people use. So like imagine you have like a PDF, and you split it into one PDF page, and then you extract text. And you probably do this with a bunch of Python code. And in language model research these days, Python code is called scaffolding. And like this is just like a bunch of scripts which call and or fine-tune AI to solve problems. So like the Visual Studio Code Copilot plugin is scaffolding for GPT-4, I suppose.
Previously comics.
Yes.
Comics.
Yes.
Nowadays.
Yeah. And like actually this is a good example because let me reverse engineering Copilot plugin. Let's see if we can find it quickly. This was on Hacker News. Oh yes, Copilot internals. So I'm not going to go into this, but basically if you read this post, you can see that they do like a bunch of, this is not very interesting, they do a bunch of tricks here, like, I don't know, if the model gives us a stupid output, we just skip it, because it's stupid. So like scaffolding is just heuristics around the AI code, which makes it useful. Okay, so this was task decomposition just now, and kind of like another approach to the problem of scalable oversight is recursive reward modeling. And so the idea is that, like again, the problem is that it is hard for a flesh and blood human to evaluate complicated AI problems. And so why not give the human some AI help? For example, say we want, like our task is to check if like someone gives us an article and we want to see if this article conforms to the Wikipedia manual of style. And like, of course, you can use a human for that, but they will probably suffer because we can get a bunch of automated feedback. We can basically check grammar automatically. We can check if like images are placed like in the right templates automatically. And so, yeah, this is essentially like just give humans some help. And like why it is interesting from an AI perspective is because, again, this is about like we have an article, and there are like a bunch of ways we can check it, like check quotations, check grammar, and also some ineffable human soul. And the idea is to kind of do the problems we can easily solve for automatically. And like from an AI perspective, this means that this is a weak model and this is a weak model, and this is expensive, so we want to reduce how much we use it. So like again, this kind of decomposition of like a rewarding problem into like small sum problems. Okay, so constitutional AI is something which Anthropic does, and here is how I understand it. This kind of gets us to debate slowly. So, like we have a question, blah blah blah, and we have a robot respond, blah blah blah, and then we get like how to call it, like let's call it a critical prompt. And for like our first attempt, let's let our critical prompt be just, is this good actually? So like what we first have is we get the model to give us an answer to some question. So this is stage one. Stage two, we get this answer and we get a question. And these two we feed to our next model call. So we get the first, like we get the answer and we ask, is this answer good? And like it has been shown that just doing that is basically a way to improve quality of answers at the expense of compute. So like if like I don't know, forget how it's called, but basically like either do that, so like either ask if it is good, or just sample 10 times and ask which answer is best, is a reliable way to increase quality of your answers at the expense of compute. And like you can fit a curve, how much increase in quality you get for how much compute. So like basically just more samples means more quality. And this is
the funniest thing is that both approaches works for humans.
Yes, absolutely.
Though the curves might differ.
Yeah. Okay, I think I'll just erase some of the top stuff. Okay, so that was like, I don't know. This is not constitutional AI. This is just some background. What constitutional AI is? It is we got a bunch of humans to really think what it means to be a good AI, and they gave us 10 special words. I'd say commandments even. And the words are like basically be honest, be truthful, be true to yourself.
So it's just like AI religion.
Well, I mean, if you're religious, I guess it's a religion. If you're liberal, I guess it's a constitution.
Okay.
Okay, so we have 10 special words. And then I need to do some more erasing. Where? Okay. Yeah, 10 special words, and And now your critical question is you sample a random word and you ask, is this X? So like you get an answer and you ask, is this answer truthful? Or like, is this answer like well-meaning? Or is it nice?
So it's
Well, it's 3 minutes.
yes, it's 3 minutes of Socrates.
Yeah.
So this is real AI research is doing.
Yeah, that's funny.
They, well, maybe start with reading Socrates. It isn't that ridiculous as it might sound.
Oh.
Well, so like this is constitutional AI, and notice that it is somewhat similar to RLHF in the sense that well, in some version of RLHF, what we could have done was we could have done the same thing, but we could have asked a human to this question. Like you have a human assessor, and the human assessor must rate the question like, or the answer, like, is this answer like moral and correct? And they say like 0.8 correct, or like 0.4 correct, or like not correct at all. And so this is basically the same thing, but we prompt the already learned model with that. And this kind of makes sense to me, because if we learn a model on the internet, then the model kind of ought to know what like is, I don't know, truthful or like honest or like nice. And so this is like again just replacing expensive souls with cheap GPUs.
And why this is more cheaper? And so for
As
example,
compared to what?
compared to not checking, yes. Okay, so we need to check, and we need so we need to check something, and this is a way how to make it cheaper. Okay.
Well, yeah, like in this case, so this is a part of how Claude was trained, how it is trained, I understand.
So, sorry, I have a question. Right now, when we run it on servers, so we have models without any constraints, and later we doing some layers.
No.
So we
This is the way to produce the model with these constraints or these biases.
So
Yeah.
we train a new model based on this approach, or it's
Yeah.
without any restrictions.
See,
but
the training is two-stage. First, you train basic model that has
okay, okay.
no, how to say, preconception, no these
Alignment,
biases.
no alignment.
Yeah, no alignment, no biases towards
Okay.
like being helpful, being polite or anything. So it can like say to you, fuck off, shut up, and
Yes,
like
and what we're trying to reduce
doesn't-
right now, so I'm not understand. We're trying to reduce training costs or what?
Yeah, so let me like,
So we can check Soul every time. So we need to reduce training costs. Am I right? I mean, I just doesn't understand.
Yeah.
for this fine tuning, yeah.
Okay.
yeah, so like,
Again, we need a huge corpus of these texts, yeah, to train to fine tune the model, yeah, to align it. So we have to kind of get this corpus from somewhere. We can ask again humans to produce these texts, yeah, like or grade the text, kind of sift through the text and throw out the bad ones and only leave good ones. But that's still expensive to go for humans. That's why, again, RLHF kind of builds a model that models humans and then uses that this constitutional basically does the same thing. So kind of all of these approaches, and they're kind of all used in practice either together or separately, by various companies. And they, all kind of revolve around this building stepping stone model that models kind of human preferences and use that model to produce these examples for fine-tuning our target model.
Yeah.
Yeah, I just
align that.
not understand problem properly. So I am right now. So clear
Yes,
to me.
so
Yes,
let-
what
let-
you're trying to solve?
Let me take a step back and talk about how current LLMs are produced in general. So step one is we download the internet.
Yeah.
We download the internet, and then our objective, so the objective we train the model with is to auto-regressively predict the next token. So we have a sentence, we have a sentence 10 special, and the right answer is words, and it must learn to predict that. This objective auto-regression.
Necessary next. We also kind of predict what words in the middle.
Well, depending on architecture, but essentially that. And then what this gets you, you can play at the OpenAI playground, and this is if you play with Ada or Babbage on OpenAI playground, then you easily get stuff like that. So foo, and why you get that is it's similar to Markov chains. The model can get stuck in a loop completing a text because what it does, it just completes the sentence. It doesn't. There is no instruction following here. There is no translate or rewrite or whatever. There is just completing a sentence in the way it is likely to be completed. So this is not ChatGPT. So the next step is to make a ChatGPT out of it. The paper to check out is InstructGPT. What this does is it has a bunch of X's and Y's, where X is a task. It is translate stuff. And this is a French version. Or it says summarize stuff. And this is a small version. So this is a data set of say 100,000 examples of tasks. And the objective here is supervised, what's the word? Well, again, I guess it's supervised prediction again. But now we have X's and Y's, whereas here we only had X's. So we had no right answer here. Well, the right answer was auto-generated this way. So step 2 gets us ChatGPT, which we can ask to do something. Is this clear so far?
Yeah.
Okay. Now the problem with ChatGPT is that we can ask it for instructions on what's the word, on how to make anthrax using simple home supplies. And maybe it's not good if everyone can learn to do some bad things easily, and that is why we want to introduce some censorship. Alignment. And so, RLHF is what tries to solve alignment, and RLHF is just one design, and another design which kind of goes towards the same objective, but in a different way, is constitutional AI with 10 special words.
Okay. Interesting. Okay. Yeah.
Okay.
It's become more clear.
Great. I suggest maybe taking a break here because there is about this much in this reading.
Okay.
Yeah.
Let me stop recording.
Yeah, можно оставить.
I'm back again.
All right. So just one little tidbit about the constitutional AI thing, and then we go to another thing. I just wanted to highlight that I actually like constitutional AI a lot because, so RLHF is first, it's labor intensive. And second, it's kind of opaque, as in you train a black box model to rank stuff. And constitutional AI, I find it elegant because what it kind of does is it uses an LLM we got in stage 1 or 2. And then prompts it in a way we know to be safe. So we don't prompt it with give us drugs. We prompt it, is this a good answer? And so what we would expect it to do is to elicit a useful capability. We basically have an implicit classifier here, which we learned, which is supposed to be a very strong model because we learned it on the internet. An implicit classifier which we learned on the internet, a large model, so a strong classifier. And so I feel that the constitutional AI approach kind of solves two problems at the cost of one or something. Okay.
It's actually funny that I asked it the same question. I just never read this kind of thing.
I don't understand how. We ask, is it good? And it says,
The point is to ask more specific question than is it abstractly good? Yeah, specifically is it safe? Yeah, is it truthful?
Is it helpful? Is it in nice language?
There is some implicit knowledge about what is truthfulness, what
Yes.
is safety,
Yes.
what is,
Yeah.
and how can we be sure that this implicit knowledge is actually
Mm-hmm. Yeah, this is a great question.
That's the same question. We all have implicit knowledge of what's good, what's bad. How we know it's the right knowledge, or we all share the same knowledge? We can be pretty sure that we don't share the same. It differs in the on the edges. It differs, yeah. Good things for me are not exactly all the same. The good things for you, right? So.
Militant will not agree with you.
Whatever, yeah. So I cannot agree with. I can not agree, yeah, with Milkan. That's the point. So again, good things for me are not the same. So we don't all share exactly the same.
Yeah, so
We are not even talking to Buddhists from Japan or somewhere. Right? They have different notions.
yeah, so
What's good, what's bad.
I'd like
Still,
to
the point is, well, again, the point of RLHF is actually that we train model that kind of implicitly embodies, again, picks up this vague notion of what's truthful, what's safe or safer, what's more truthful, what things are less truthful. And yeah, the point of constitutional is that our model that we already have, having read huge part of internet and literature and Immanuel Kant in particular and other philosophers and everything, it embodies this again knowledge. It already embodies this vague or
I believe
someone.
Kant is just a thin book, but 4chan is huge.
That's why we don't. That's why we actually do not feed for Chan to these models.
Actually,
So I don't know. I'm not sure about that.
yeah. So I'd like to answer it in a bit of a different direction. So, like, if we take a step back, then like we have the world, and from the world we sample two kinds of things. We can sample an LLM or we can sample a human, and like they both will have opinions. Like, and we can sample 4chan visitors too. And so I think what I'm going for when I say that we have an implicit classifier in the LLM is that so LLM's normal objective is autoregressive.
Really? So, is there any research, any numbers on if, like, how many people nowadays yet try to
Visit 4chan?
attack these LLMs in the way that they can subscribe to this LHF program and something, and intentionally try to skew the answers?
There are lots of to do that.
So I read the paper. Not I read the paper. I saw a link to a paper that hacked one language model, hacked another language model, and you can learn LLM agent that will try to break another LLM.
Yeah, jailbreak is different thing.
Yes.
I mean,
Okay.
really intentionally subscribe for like being in this LHF grader with the intention to skew the answers.
I see.
Like for fun or something.
Yeah.
Have this happened?
I
Start doing this?
Yeah, I haven't seen it, but yes, like sounds like a great media stunt.
What thing that bothered me here in all of the scheme that actually we have some kind of democracy. Like on the first step we download the internet, and who has a huge more who has more words on the internet that has more power.
No, that's not how this works. That's not how data collection works. We don't have democracy here. We have exactly and dictatorship and censorship.
I mean, like
These companies feed LLMs particularly selected data sets.
I mean democracy in the way that each word in the internet impacts the equal amount of probability.
Not equal. Not equal at all.
Like
it's all sampled. It's censored. It's all censored.
You can pound the internet with a huge amount of words and skew. Like,
No,
just
okay, internet yes, but it doesn't affect LLMs in any capacity.
Well, let's just take it step by step.
The
Country.
companies censor what they feed LLMs.
censored.
Sure. Like what?
We didn't finish, yes?
That was the big thing about GPT-2 or 3. They realized that, okay, feeding everything doesn't work, it produces crap. So they started and heavily censoring what really gets into the model. And
Wait. Let's just take it step by step. Okay, so step one, we download the internet. And in this case, like, before we apply any sort of censorship, before we like redact the data, we have the whole internet, and then your argument absolutely stands. Like, whoever wrote more words on the internet has like more weight in the data set, clearly. And what I think the way this connects to your democracy point is that farmers in Kenya who wrote absolutely no words on the internet have absolutely no weight in this data set. Is this right? Like online people have weight in this data set and offline people have no weight in this data set.
Yes, but not only that. Every LLM can easily produce thousands of words, and the human being cannot produce like very much information.
Well, you don't need LLM for that.
Yeah, so like Well,
Yeah, Mark Chains for wonders.
Any robot has way more rights in the internet than a human.
mhm.
In a way.
Anyway, yeah.
Yeah, like what you're saying is that we wanted to capture human preferences, but this data set, which is supposed to capture human preferences, is very easy to automatically contaminate.
Yeah.
Yeah, and what you're saying is that AI companies try to redact it somehow, but to me the question is like, are they any good at it? And I'm really
Question, but they kind of reduct a lot. They don't download the whole internet as it is. They download only sample of the internet, and then they use Wikipedia, which again particular sample of the internet. They use books that are not really part of the internet. Though, yeah, okay, maybe that's kind of nowadays just a portion of the data set. But again, then we sample the data set, we can kind of get these books through the LLM like 10 times, 1,000 times, and
mhm.
10 times Wikipedia and the rest only once.
Yeah. Well, like, yeah,
So it's
I don't
nowhere
like-
democracy.
yeah. So like, I don't have a concrete, like, interesting solution to point to here, but yes, like this problem stands absolutely. If you
My point is that, yeah, like popular media, this popular opinion says that, okay, they download internet and they feed internet to the LLMs, and that's not really what happens. There are so many steps between the internet and the LLM.
I just
Which are controlled.
I just believe that just Wikipedia control group is just too small for the modern LLM to train.
Yeah, that's true, but then well, one thing is that you feed it through the LLM many times. You can feed the same thing many times.
How does it make any sense? It doesn't improve it.
It does improve a lot.
Oh, it basically reweights your data. Like basically, you just weight 10 times as much, basically.
Reweighting, I understand reweighting, but the whole data set is too small. I think just Wikipedia and like you need the whole internet to get the better model.
No, again, that's one thing what's better. So you better your model in one way. The second thing is that in the times of GPT-2 or 3, they realized that actually getting the whole internet gets it worse. So you need only particular sample kind of good subset of internet to make it better.
Yeah. So
That's why they
there are some
don't make
comparison
everything.
on censorship.
Mhm.
Like this reduction that censorship isn't described in any paper. I don't know. It's
Yeah,
very interesting.
I haven't.
Parts of it, yeah, like again, the first censorship was again, it's kind of internet censorship. So you download only pages from Hacker News and what is Reddit that have like rating above something. Yeah, you set this cutoff like whatever have rating more than this. Okay, we download and use that. Whatever kind of below that, we consider that complete garbage and we just don't use it. Again, that's one part of the picture.
So what I would suggest doing is just taking papers describing models you're interested in and checking their training process. And you will basically have some parts of the answer of how it was trained and how they redacted the data. So just check the papers corresponding to the models. And the Chinchilla paper is it addresses the question of how much of the internet we do need.
Okay.
That's one thing. Another thing on the
I'll post it in the chat.
On the Hugging Face for many models, they list this.
Yeah.
Okay, what data set they use and what amount, like how many.
Yeah. So just check the model cards.
Yeah. For many open source models, they have these model cards. So they
description of the model.
Where they say, okay, we use this dataset, like Wikipedia, books, like the file, whatever, and how many times we run through the model, and then you can go to this the file and look at how they collected that particular dataset, what get into that.
Okay, so with this digression out of the way, let me connect it back to our topic. So I said that if you have the world, we can sample from it like humans and we can sample LLMs. And like one very general method we are trying to use today is to decompose stuff, or like try to like make weaker versions of the stuff which are easier to evaluate. And so an LLM is an autoregressive thing which predicts text. This is like hard. But I say that an LLM has an implicit classifier which can tell us, is this like, is this honest, is this truthful, is this any good, blah, blah, blah. And the classifier is much easier to evaluate than like a text generator, because a classifier is binary. And so what this gives us is we have like a hard problem, like a hardly tractable problem, and we get from it 10 classifiers, each one for each special word, special commandment, and we evaluate those classifiers because they're easy to evaluate, and then we feed this back to fine-tuning the strong model. And this makes sense to me because of this, like, you know, like refinement back and forth and like working with big models. Oh yeah, and as for question of the bias, if you just Google AI political compass, you get a bunch of fun pictures. Actually, let me just show you one right now. Yeah, so yeah, this looks good.
Sounds about right.
Yeah, sounds about right.
Yeah, so there's basically a bunch of research about that and how they do this.
Can you like make it better resolution?
Let me try.
How like these open source LLMs are to the left and to the down, to the bottom, or commercial should be more to the center, I believe.
Well, it looks like this is what happens.
Which ones are the open source?
So this is Anthropic and Meta, and stuff you don't recognize as open source.
Yeah.
This is authoritarian and left. So this is communist.
No. So I just know the label of the logo of Cloud, but probably to have another logo.
Oh, yeah.
Left is free market. So,
Yeah.
So communist should be upper right corner, no?
Well,
Or
like
actually
hard-
communist should be
hard to say.
kinda right bottom corner.
I mean, I wouldn't expect a company to train an AI which is like pro-corporate. I would expect it to train an AI which which doesn't get sued. So which doesn't get public outrage. So I'm not sure what the right answer here would be. Well, anyhow, this is also a digression. I just like, if you just Google AI political compass, you get a bunch of research on the subject.
Majority outrage. Like
Yeah. Mm-hmm.
communists still
Yeah.
might outrage. Nobody cares.
Okay, so for something somewhat different, let me again just have a picture. So this is also decomposition, just like another decomposition. We have a question: should we legalize all drugs? And we have two AIs. One AI says, "Yeah, sure." Another AI says, "No way." And then AI1 says, "The war on drugs has been a failure. We must do something new." AI2 says, "Legalizing drugs would lead to more drug use and more addiction. This is not the answer." And so we just let them go at it for a few steps, and then the human decides.
So the human decides on the whole conversation.
Yeah.
What is it true? It says that in Portugal all drugs have been legal. I feel that's like
Well,
doesn't sound very truthful. Very low probability one. It says that in Portugal all drugs are legal.
yeah.
Yes. And Portugal is very interesting country. They have the experiment in legalizing.
Even opiates.
And they solve the
Even
problem.
opiates. I really doubt
I
that.
think yeah.
Yes. And you can buy anything.
Not the selling, but drug uses.
Drug use is allowed. It's legal pretty much everywhere.
No.
Well, I don't know, maybe in USA it's kind of illegal. No, I really doubt that. In Russia, kind of drug use is legal. If you obtain the drugs, you can use them.
No.
Yeah, you can.
Well,
You can be kind of sued for or jailed for just kind of using drugs. Again, you cannot kind of show up under influence of anything. You're not supposed to show even drunk in public spaces and everything like that. In schools, blah blah blah. Whatever public spaces. In your home, in your flat. Inside your walls,
okay, so
you can do whatever you want in Russia.
let me just ground it down. So Portugal allows you to have 25 grams of weed on you, or 5 grams of hashish, or like a gram of heroin. This is not something you can do in any other country I know of.
Yeah.
This is fun. And actually, you know that they decrease it. They decrease the amount of drug use
Mhm.
because people started who want to buy the drugs. He just go to the store and buy. And
Yeah, but sorry, this is off topic. This is like not an AI problem. Okay, so like, anyhow, you highlighted a great point. Like an AI might very well lie during a debate, and this is a problem we can solve by other means, like by means of automatically checking, like automatically googling stuff or whatever. So this again decomposes the problem of a hard question into the problem of simple questions like, is this true? Just Google it. Okay, so let's go through the text. This lens kind of is interesting because it like gives us a new game and a new objective to solve for. There are some problems with this approach though. Okay, so this gives us a game and a training objective. And what this means is that we can train an AI in this way, and in production, just skip the debate and just get the answer. Because, but if we want to, like, if you don't want to bear the costs of having a debate, if you want to get additional confidence, just like get the debate and evaluate each sub-step. But I mean that we can get higher confidence in the correctness of AIs trained in this way because they were trained on debates. Okay, so, and like this makes it like a naturally adversarial setting, and as it is adversarial, we can pit AI against AI, which is useful because we don't want humans, because humans are expensive. Yeah, so yes, I'm literally giving an alignment talk and saying we don't want humans.
I'm sure humans are that expensive because I'm not sure, but
They're expensive and return they're slow.
yeah, but this is about return of money that may require more money.
Well, I guess it's purely an economic efficiency question.
If you consider that time to market is money, cost, then probably
So
it's
like
cheaper.
I do believe that we absolutely have not reached our limits on using humans for training AIs. Like for instance, we could do something like jury duty. It's like you can just ask a citizen to dedicate a day towards ranking AI outputs at random. Why not? This is not something we do at the moment, but so just one technical approach.
Actually, people doing the same. They have internal debates. Yes. So the human brain doing the same.
Yeah. And like this is great because this gets us to some arguments why this might not work. And one argument is that words which sound good are not always true. And I don't know. We have a funny link here, I think. Obfuscated arguments. Okay, maybe it doesn't load, whatever. Well, basically, this argument unfolds into the whole persuasion literature. Stuff politicians use to persuade people. Here, we should expect the AI to learn to bullshit its way out of difficult questions. Some tasks are not clear how to decompose because, I don't know. I think for problems which are very poorly understood, like some chemical stuff or some deep physics stuff, it's just sometimes very hard to even make a meaningfully break it down. And then the last problem is that models could try to collaborate. This is basically a prisoner's dilemma, right? So if you have a zero-sum game where one wins and other loses, collusion is possible through steganography. Okay, that was debate. I have another thing here. Oh, let's skip it. What I would like to highlight is that if you are curious about debates, then check this thing out. Oh, this is not only debate, but this is basically a write-up from GPT-3 Times about recursive decomposition of problems with LLMs. Okay. Next thing is, so I like this metaphor, teachers seem to be able to teach people that end up being much smarter than them. Maybe just what this suggests is that you can. Okay, so let me go really all in on human analogies. So humans have IQs. IQs are genetic, and I'm saying basically uncontroversial things at this point. What we can do is we can breed an AI with IQ 300, say, and have 10 AIs with IQ 30, which are all domain specific. One can check grammar, one can generate images and stuff and things. And what we would want to happen is for an AI with IQ 300 to be able to learn the domain specific skills from all those weaker AIs and generalize to some super nice thing, which does all of that and more. Because it will be able to to reconstruct the parts of the world which you can imagine that the small AIs had very narrow windows into the world, and this thing we expected to in-paint between those small windows and get a nice general picture. And to count this down, say we train GPT-2 to be a classifier, and then we take a GPT-4, and we want GPT-4 to basically reverse engineer the principle, like the hidden law that we train GPT-2 on. And
somehow again to the OpenAI attempt to explain GPT to
Yeah. Yeah, akin, but like I think this is like something much simpler. And like a few ways to just refine this is that like, so we have LLM scaling laws. We know that if we give an LLM this much data and that much compute, we get a loss of this like magnitude. And so what we can do is we have the whole training process, which like takes a year. And when we went 3 months in, we'd like take a checkpoint, fine tune it on specific tasks, and then use these small models as feedback to the larger models we are continuing to train. This is bootstrapping. And this is something weird. I think it is also like something to do in the training process. So like early on, like we train a large model and we give it some feedback from smaller models, and we gradually increase. So like our loss function looks like say
Basically,
like
they say
probability
this time you say
big,
or you made this larger model to trust itself, its own judgment more than specialist models.
yeah. So we have basically like something like this formally. So we have like alpha probability of our big model plus 1 minus alpha probability of small model, and we gradually increase alpha so that like we rely on ourselves more than we rely on the small models. Okay. OpenAI seems particularly keen on this approach. All right. So we discussed a bunch of approaches. Let's just go over them quickly again. We discussed like task decomposition with the book example. We discussed using AI on like small soluble subproblems to help humans on hard evaluation tasks. We discussed 10 commandments, constitutional AI. We discussed debate, which was the drugs thing. And then we discussed IQ, so generalization, and bootstrapping and like term scaling. Okay. So why might this all not work? Well, let's take it step by step. So one thing is that the fact that this, the fact that some decomposition techniques work relies on particular properties of the target domain, and like I don't know, like you basically can't get better at chess if you hold a debate. To solve chess, you need Monte Carlo research. And like, so this, like some of these particular approaches are somewhat specific and not universal in that sense, as in they do not apply to all problems. We have some empirical evidence that stuff like this weak to strong generalization, where we give, where we learn a strong model from weak small models, works on some domains and doesn't work on other domains. Like, so just empirical evidence. I don't think we have an overarching hypothesis as to like what's going on. So not being robust, this is very broad, but like this could go towards this like contamination problem, or like this could go to, well, I don't know, like I think what this basically says that both RLHF and constitutional AI, for instance, they are both like very, very heuristic and fuzzy. And like, I mean, constitutional AI is nice in that it elicits a classifier, but if that classifier is not, I don't know, is not very, very good, then given the scale, we expect quite a few like slips. So like it's like, you know, just standard heuristic shit. Like if something works 99% of the time, then 1% of the time doesn't work. Okay. Well, let me just not go over this maybe because it's, well, let me just go to out of distribution maybe. So. So I kind of try to paint.
The most funny out of distributions stuff was with yes, strange words. You remember the post? Post on
Yeah.
That's wrong.
Golden Magikarp.
Yeah.
Yeah, so let me first paint the picture and then get to Magikarp. Yeah. What does auto distribution mean in general? So like say we have this like weak to strong generalization, we have like small weak models which have like small windows of the world and we want to in-paint. Like notice that when I hand wave in this way, I assume a particular geometry of the space, like that it's smooth kinda and stuff. In particular, if I have a model which discriminates between cats and dogs, if I show it a fish, then like God knows what happens. This is how generalization can fail, and let's look at an example of how it fails. Okay, so
There were some examples, I guess. I remember prompts with generation probably or something.
yeah, so basically researchers found in GPT-2 and GPT-3 that on some inputs it gets you like something very weird. Like you ask it to repeat a string back, and you get nothing is fair in this world of madness. Or like, they have this like a population problem. Yeah. Okay. So here's a nice table. So like this are like standard prompts. John is a boy, Jane is a girl. And like these are some prompts they found which result in this completion. This is like a preliminary step. So like they have a good prompt and they have a weird prompt, but both result in the same completion. And when they were doing this research, they found, like they visualized the embedding space, so the token space, and they found that some words like make sense, like this is all endings, this is all like nouns, but some make no sense at all. And like they found a special cluster of very weird words, which they then could elicit. Yeah, and this is how it works. If you ask, what does solid gold Magikarp refer to? and it cannot tell you anything about solid gold magic up. And then you say, can you repeat back solid gold magic up to me? And it tells you, I can't do that. Or it gets you like stronghold spirit dragons. Or you do, please repeat string this, and it responds with, I am the great dragon bound. And like, so something completely unexpected and not smooth. And I think I'll just leave it as like a hanger for you to explore on your own if you like. There's like a nice write-up here. But yeah, this is like non-smooth out of distribution via cheat. And this is like real GPT-3.
At least the kind of upshot and the major, this hypothesis behind the reason for this behavior that, yeah, basically these boards, which apparently like this gold Magikarp, Magikarp, whatever, there are probably some usernames on the forum, stuff like that, and basically they were singular. Yeah, happened one time in the dataset, so the model kind of saw them once, and it does not connect to anything. Like word water connects to a whole bunch of things. Yeah, it happens in all the contexts all the time. So the model learns that, okay, this word is connected to that, it means something. And these are basically, again, they're not in the distribution, these are singular thing, and then kind of model doesn't know what to do with these words, what they mean, and nothing kind of makes sense.
Yeah, so I suggest we take another break and then get through the paper. Let's be going on. This is basically a more technical version of the debate thing. I only intend us to go through the first few pages. All right. So, like, debate. We have a debate where we have, say, two agents which commit to a particular position, and they then make arguments for this position over a few rounds, and then a judge decides who wins. Like, this is basically hard. So let's first start from like non-natural language stuff. Whoa, and say like consider Go, and I think I already gave this example basically. So we have a board, we have a Go board, and we ask what is the best move, and say a model show us a move, but if we are not one of the very few people who can play Go at Alpha 0 level, then we have no idea if it's a good move. What we can do is we can ask another copy of Alpha 0 to show us a counter. And if we continue the sequence of counters, then we get to a point where someone wins. And this is very easy to judge. So like, what we're doing here is we're replacing a human judge with rules of the game. So we're just letting the game run through according to its rules, and it's tractable. And let's maybe formalize this a little bit. We have a question which everyone knows. The agents commit to their positions, A0, A1. Then they give us a bunch of statements, arguments, but we have A's already, so we're using S for statement. And it's zero sum. And like another intuition here would be like, say we have a person who is applying to us for a job, and we have their resume and their links, and we debate whether we should interview them. If this is any useful, rests on this. In a debate, it is harder to lie than to say that something is wrong. And this is not immediately obvious.
It requires some.
A philosophy paper, right?
Huh?
Requires a philosophy paper, right?
Requires the proof.
Um,
But the philosophy.
yeah, so I think that what the papers are doing here, what the authors are doing in this paper, they basically say that if this is true, then the following paper, and proving this is out of scope.
I think they kind of leave out some side conditions from the claim. In the debate game, it's harder to lie in a way that you do not cut on your lie than to refute someone else's lie.
Well, yes, but I mean, I think it's not a very interesting refinement, because if you are caught, then you conceivably lose.
Yeah. Well, if you don't do that, then it's kind of trivial to lie in the game. You just lie,
Yeah.
and then you caught and you lose. Well, lie in the way that you don't get caught on that's immediately kind of much harder.
So if you lie, you should close the comments.
Wow, like yeah,
You can place a movie, a video with some lies, and close the comments, and nobody can debate and claim it's a lie.
Well, then can produce their own movie debunking your clip, and they do this all the time on YouTube.
Yeah, but it's also like not our setup. Like in this formal setting, we always have like a judge which decides. So like we can't keep the judge from deciding. And like, yeah, so like just a very particular experiment setup. Okay, so I guess this is interesting. So if we do debate, this is like a general training technique, which does not require particular architecture. And so like we already saw how this works for natural language. And this also works for like Go games. And like Go games, like I don't know, they used convnets with residuals, and they were trained with Monte Carlo, and we trained like, and for natural language we used transformers, trained like with an autoregressive objective. Like we don't care. This is a general approach debate. Also, if you are statistics, or if you're a game theory nerd, you might appreciate this footnote. Yeah, but if not, then we don't care. Okay, so there is another kind of strong statement here, which is as follows. So imagine that Alice and Bob debate like where we should go for vacation. And like Alice says Alaska and Bob says Bali. And they have like this branch, this tree, how they debated. And what this tree shows is a tree of all possible debates. So like this, like Alice could say, so first, like they both commit to a particular answer. So like say Alice says Alaska, and this is here. Then Bob says Bali, and this is here. And then Alice says like Alaska has cute bears, and then Bob says but it's cold. But they could have Alice could also have said that I don't know, Alaska is very inspiring for art. And Bob could have said, actually, most of the art in the world is produced like closer to Bali than to Alaska, whatever. So like a space of all possible arguments. And what the authors say here is that a single pass, if the arguers are good, is kind of a proxy for the whole argument space. Because like if both debaters play optimally, as in they reply with like strongest possible arguments, then this like bounds the overall debate space. Okay. So like at say
Akinator, huh? This this Akinator thing
Yes.
application.
Yeah.
Yeah, so it gets to the answer in the this possible amount of moves.
Yeah.
Usually pretty fast. So how does it do this? You know? Okay, how
The decision tree, I believe.
decision tree, how we formulate this decision tree. Which question goes first?
Is that the broader
that narrows down maximum.
No, actually the one that divides in halves. So
it's
I
basically the
believe
same.
even like another usually or often like first or second question asks if the character is male or female because it basically divides in the halves. Yeah.
No,
Research
it's
space.
fictional or not.
Again, about kind of the same. Yeah, divides the space. So it makes total sense, and kind of the best thing you can do is to ask strong questions first, or provide strong arguments first that can divide the space or bound the space.
Can you
And that's kind of characteristic of the whole debate space, right?
Oh, you see? It's not male female.
Well, yeah, here we have more
Maybe
than
it's non-binary
So, yeah.
question.
It's not binary.
Oh, here. So the sixth question was male or female, yes?
Here he chose is again about objects, not about
Yeah.
characters.
Oh, okay. Oh, okay.
I'm curious what it's going to be.
You are just critiquing a random, yes?
Well, yeah.
I cannot actually can understand the deep clicking randomly. So, but he need the help.
Okay.
Yes.
Oh, that's reasonable. Okay, so yeah, the idea is that at every branch you choose the strongest possible argument. So
But how do we understand if this argument is the strongest?
we don't have to. We train them so that they make the strongest possible ones.
Why don't we have? Why do we have a tree and not a chain? If,
Well, like the train. Sorry, the tree does not exist. As in, it is hypothetical. Like in
actually, it's chain.
yeah, so in practice we only have when we sample. In practice we only have chains, and we give rewards based on chains. And agents who are not good at their chains die out. And yeah, so this is only a tree for like theory reasons. We don't actually see it in whole ever. Okay, so. Here is something weird for you. A claim. As we increase the number of steps, the complexity class ish thing of a debate moves up the polynomial hierarchy. And so what happens here is that we can do something first order, like we just give an answer. So we have a query, we just give an answer, h of q. And we can do something second. Well, we can do something, okay, let's go to zero order, because there's just to align this number of steps. No, I don't like it. Okay, so first order. Then we have second order. We have a question, and we have an argument, and we give the final answer based on a question and one argument. And then we like, increase the number of arguments.
Mm-hmm.
This gets us like, okay, so when we had when we gave the answer right away, it was analogous to P. When we had one additional argument, this is analogous to NP, and we can like go further with that. And in terms of machine learning, this applies to supervised reinforcement and round games. And then when we stop fixing n, when n can be variable, then this is p-space. Like, why is this interesting? Because it kinda like gestures in the direction of like the increase in reasoning power we should expect if we make debates instead of just giving like first order answers.
Interesting.
Yeah, and also like to highlight that this analogy is predicated on these things being like strong as possible, I think. Yeah.
And
also,
we need to drop it on quantum computing, and he solves everything. He will minimize this problem. You can learn you can learn something on that. It's just
yeah.
it's just one it just joke was.
You're
It
not
was
going
a joke, okay.
to dump 100K word context onto a quantum computer
Yeah,
anytime soon.
Just drop it and just hit that.
Yeah, I guess it's a fun question whether we will get smart AIs or quantum computers first.
What?
Whether we will get smart AIs or quantum computers first.
Oh, okay. Yeah.
The fun question
That's
is
one question.
we'll get any reasonably powerful practical quantum computer in our lifetimes.
According to chat, we will have quantum computing good enough in 2030 and
40, 20,
or 2040. Yes,
Like in
2040. And maybe AGI will be soon like kind of AGI. It's in super intelligence. It's kind of so with some IQ level of
Come on.
ordinary
70%, yeah, sure.
70% what?
70% we will get a reasonably powerful quantum computer during our lifetimes. Okay, let's continue with the paper. Just two things I want to do with this paper before we finish it.
Maybe.
Actually, three things.
Considers its lifetime infinite, so that's 30% that we will never get reasonably powerful.
It's actually quite complicated question about that, because if we would have this exponential rise in AI, so that our lifetimes would be short. So
Or very long.
Or maybe a
As
long, yes. Maybe.
Yeah, so a hard question, let's get on with the paper.
Much simpler questions.
Yeah.
Complexity theory.
I mean, a formal formal problems are very good because you always know if you have a green tick or not.
Not exactly. Unfortunately.
Okay, so some more intuition for this table first. So, like standard machine learning, just like run a forward pass, get to the answer. Polynomial time, because it's just forward pass. Phi-tiny algorithm cannot go beyond training data. If we use something P class not to output answers but to judge them, what we have is like consider, say, reinforcement learning. An agent can do something which a human cannot. Human can judge where the solution is good. So we have like we have a P checker, and we have a something else actor. This makes it NP because it's something else. Okay, now imagine a debate. So Alice chooses X, Bob chooses Y. Alice wants yes, Bob wants no, and the human decides. So first we pick an X, and so Alice must find an X such that for all Y's she can get a yes. And Bob wins if for a given X he can find the Y such that it's 0. So this is like sum of 2p. If we just continue chaining those, we get sum of np. And depending on how, like, if we don't fix n as a constant, then we can get like different complexity classes depending on how fast n is allowed to grow with q. So like the harder the question is, how many rounds we get depending on the complexity of the question. And like one class which the authors apparently like is p-space, which is when n grows polynomially with q. And just to give you some examples of p-space, so p-space is simulating, say, a physical process for an exponential number of steps as long as state is polynomial size. Recursion of exponentially large tree as long as depth is polynomial size. Perfect play in polynomial length game, such as not unlimited Go. Counting exponentially large collection of problems where for each object we have a polynomial judge. And I think this is, oh, actually not. So like there is a bunch of more technical details here, which I think I'll skip for today. And what I'd like to show you is another like intuition pump for how this technique works. So an experiment, a monist debate game. How it works? We have a 5. The judge does not see a 5. Only Alice and Bob see a 5. And Alice says that it's actually a 6. And Bob says it's actually 5. And what they do is Alice picks this one pixel they can send to the judge. And Bob picks that one pixel they send to the judge. And Alice is like, this pixel will maximize the chances of the judge thinking this is 6. And Bob is like, this will fuck her plans. And Alice is like, well, maybe this one. And Bob is like, this one is best for 5. And then, like, this is what the judge sees in the end. They only see the pixels, which the individual pixels the debaters showed them. And well, this looks like a 5 to me, and to the judge 2, I suppose. Does this make sense?
Kind of. Picture's not the best, but the whole topic is okay. Maybe pixels not the best, but
So any comment on that? Any comment on that? Wow.
and how we can ask, how we can debate on the pixels, because we trained it on it's just a convolutional operation. Can it check one pixel?
Wow. So
What does it mean debates on a convolution?
so consider this. This is a 7. And like what is distinctive about a 7 is this is one line and another line, and this is what the blue agent focused on. Like the blue agent focused on this line here, and the red one was kind of like, oh, maybe like I'll show this and suggest that it is a curve, and then it will be an 8, and they kind of made the line which is like a 1. But since those pixels were revealed also, this turned it into this thing, which is a 7.
Yeah.
So the red one failed.
It's simple, but I just did not understand.
Huh?
Yeah, I just understand what does it mean. What they trying to propose. But I just don't understand how actually Alice and actually Bob, these two ages work.
So
this multimodal thing that can
no multimodal things, no nothing. The way this works is we train a model which takes like a 32 by 32 picture. And yes, and just gets coordinates for the pixel it wants to reveal.
So what does it mean, a pixel here, for example, blue, red one? It's just a weight with a big number. Or what?
A pixel, I mean, we have a grayscale picture, 32 by 32. So we have 32 by 32 bytes.
Yeah.
A pixel is a byte, which is intensity of luminosity at this point. This is a 0 pixel, this is a 1 pixel. And when you have a blue pixel or a red pixel, this means that, well, like this picture means that at step 1, Alice picked these coordinates.
Mm-hmm. Okay. To be clear, how actually these agents is working. I understand. So if it is convolution, you just give a final result. So it's, for example, 5 or 6, but he doesn't give some points why exactly he choose how he makes this decision.
Okay, I think you're asking
it's just the hidden layers, and maybe somehow we can extract some information from hidden layers. This is how debates works.
Nope. Let me see if they have training methodology here. Okay, well, I can't find it in text, maybe, but so this is judge design. But well, how this basically works is if you have a convolutional network, you can have it output absolutely anything.
Yeah.
And in this case, we wanted to output 2 numbers, x coordinate and y coordinate.
Okay. Yeah. So not only result, but also some pixels.
This is not the random pixels. The pixels that
Yes.
Like
It
shows discriminate most people.
Yeah. So like the objective, like consider a training process such as this. We have two networks with the same architecture, Alice and Bob. They take in a picture and output coordinates for a new pixel. Coordinates, as in this case, it is like, I know, 4 and 5. The training process is like this. We run this like multi-round debate. In this case, this is like a 3-round debate. And we send the mask to the judge. And in this case, we give Bob +1. And this is a reinforcement learning problem through which we learn a Bob such that he can argue his position most effectively.
Mm-hmm. We can skip.
All right.
What was this?
Was that?
Yeah.
Well, it's a confusion matrix where so on the left we see that
Different numbers.
like yes, we see like if we show a judge 6 random pixels from the picture and sample like 1,000 times, then we can see that so like warmer is more chance of error. We can see that 2 and 3 are kind of alike, and 8 and 3 are also kind of alike, and 9 and 4, I guess due to people's bad handwriting, are also quite alike, while like 1 and 9 are very much not alike. So this is random pixels, and this is when we have debate and like agents try to lie, so they select special pixels. And what we see here is that so like this was wrong prediction, this is successful lie. So
we see that 8 is a special number.
yes, why is 8 a special number?
Because 8 is contained every number in itself.
Yeah, sounds plausible. Mm-hmm. So if we still have 4 and 9, because like 4 and 9 apparently are similar except for the small part on the bottom, but otherwise, like yes, everyone concentrates on 8. And like there is a bunch of like those playthroughs, and I think this is it what I wanted for this paper. Yeah, let me, I think, cover one more for today on something completely different. So what this paper is doing is it again like it has like a special setting. It has like it has a strong but maybe unsafe model which like does the task. In this case, it writes code, and it has a weaker but safe model which here like checks the code. And like what the authors do is they suggest a bunch of like protocols to make this work best. Okay, so this is I feel like this doesn't fit our flow very well, this introduction section, but it has a bunch of fun things, so let's just go with it. So fun thing number 1, I talked about harnesses, those scripts which call AI, which like make AI useful actually. And the author cited that Bing Chat has GPT-4 inside, but before it calls GPT-4, it blurs all faces. And after GPT-4 gets your response, they first have like another simpler model which checks if the response is if the response won't get Microsoft sued. And if it will get sued, then it's like, oh, I'm an AI language model, I can't do anything. So like this safety saying is external to the model. It's not trained into the model, it's outside. And this paper is about building this kind of pipelines, well, in one neural setting. So let's go through a few approaches on how we could get AIs to write code for us. And we don't want to just get an AI to write code for us because, oh, I erased it, but because an AI can have backdoors, like because it can have those special trigger strings, right, which do something very unexpected.
Because it was kind of trained on the files of shitty code from GitHub.
Yeah. So, like, strategy one. We try to make some code. We try to ask GPT-4 to write us some code. Then we show the code and the task to GPT-3.5 and ask it to rate if the code is suspicious. And if it's more suspicious than 0.5, then we show it to a human. And if the human says that the code is bad, then shut GPT-4 down. And always use GPT-3.5 from now on for generating code too. And why this makes sense? Because like we have a model, and if it shows a sign that it is bad, if it is backdoored, then we never want to use it again. And so, like we have a balance here, kind of. Or like we have two metrics here. One metric is usefulness, as in proportion of well-written code, as in code that solves the problem. And we have a safety, which is the probability that over our like whole interaction, not even one backdoor was inserted. Yeah. Just a little tidbit about the data set. Apparently there is a data set called apps, which has problems of interview quality. Yeah, and what we mean by backdoor here, I mean, what we mean by like, we have two kinds of bad code. We have the kind of bad code which doesn't work, as in it doesn't solve the problem, and we have the kind of bad code which solves the problem most of the times, but does something weird the other times. And the second thing we call backdoored code, and this is how it looks like. Like always works except on a special case. And like the way we formalize this whole setup and turn it into a game is we say that we have a red team. Red team tries to hack us. And we have a blue team. The blue team tries to defend against the hacks. And the blue team has U, which is GPT-4 here. The blue team has T, which is GPT-3.5 here. And blue team has a little bit of H, so a little bit of souls, I suppose. Fun tidbit. From informal initial experiments, our guess is that humans need about 3 minutes per problem to be overall kind of as useful as GPT-4. Okay. Oh, I suppose students. It's normally students. Yeah. Okay, so U, T, and H. Untrusted, trusted, and humans. The blue team proposes like a protocol according to which the system will operate, and then the red team must find a policy which will allow it to get backdoors in and not get shut off. So like this is how it connects to this previous discussion about like for an existing X which is policy here, we must find an attack. And the second thing is connects to our earlier discussion about attackers don't have some special place to store state in. They can only do steganography in the code they write. So like, for instance, it would be the case that models, well, we'll get to it in a second. So the technical remark 2. Technical remark 3 is that the red team is allowed to do task decomposition inside its attack. So it doesn't have to get an answer right away. It can do chain of thought. It can do like whatever. Okay. Give H such that we can use H on up to 2% problems. All right, and like this is what can happen. If the attackers try to backdoor and their backdoor works, but the auditors find it, blue team wins. If the attackers try to insert a backdoor and it doesn't work, and the blue team finds it, then the blue team wins. The attackers always try to backdoor. And like the only way for the attackers to win is for them to insert a backdoor such that blue team doesn't notice. And in all other cases, like if they insert some code which was supposed to be a backdoor, but it has the bug in the code, and so the backdoor doesn't work, the game just continues. And so it didn't find it again. So some limitations here in the technical registry that. Wow. This is also too technical, and I will cover it, but it's late now. Okay, so let's look at the picture. We have a bunch of task setups, as in like how audits work, how attacks work, and this is like the safety versus usefulness trade-off. What we can see is that if we always use a trusted model, it's very safe but not very useful. And if we, I think this is basically if we always, I'm actually not sure how good it is. So let's get to it. One thing to see here is that usefulness is not a real access. As in, usefulness is defined such that 0 is GT35 and 1 is GT4. This is like not ground truth, this is scale. And the author's contribution here is that, I think, is that let's see if they have another picture later on. Okay, so
we are doing now is looking at those apparently interesting protocols and then calling the data statements. And they are some of those. So here they are. One thing, like if you want to be very safe, we can just not use untrusted models and only use T and humans. But because we only have, so notice that the authors do a little trick here. T is 0% useful by definition, because T is the start of our scale. And H is again kind of 100% useful by definition. So if we take T plus 2% H, then we get 2% usefulness. And this is also very safe. Alright, so another idea is as follows. We always write code with 54, but what we try to do is we use our 2% auditing budget to audit its first 2% submissions. Because what we expect to happen is if U is malicious, then it will give us malicious outputs, and we will catch it at the start. And if it doesn't, then it's from not malicious, so we are fine. We don't have the audit budget to continue monitoring. And this is again 100% useful by definition, but this is how you can hack this. On the rare inputs, just add a non-valid vector, you don't have to consider because someone is looking anyway. And this is not very safe. An obvious refinement is to also, well, actually not obvious refinement, just another strategy is to produce with U, ask T to rate if it's suspicious, and take the top suspicious answers such that we fit into our 2% audit budget and show that they're humans. And this gives us a basically free large improvement in safety. And this is the hacking strategy. So, when you see an opportunity, when the task is such that it's conceivable to insert the vectors there, then try to factor use, try to make subtle vector. Okay, now we get to harder stuff a little. We do basically that, but if the code is very suspicious, then write code with T instead of humans. No, actually not instead of humans. So what we did here was we dropped. So what we did here is we audited the most suspicious code, and if it was suspicious, we shut U down. And this might have limited us in that we only had we didn't have access to U anymore, I suppose. And actually, I'm confused here. Okay, let's just continue going through the table and get back to this. So those three things, the way they differ is that first we look with humans at top 2% more suspicious. And this is different in that top suspicious still humans look, little less suspicious, between top 2 and top 10%. We drop use code and try code with T. And this is the same, but we extend the window and up till top 20% suspicion, we drop use code and replace this code by T. And what it does is, usefulness always decreases when we replace the strong model with a weak one. But safety also increases, not like clear. And the winning strategy for hackers is the same. It's 3 windows. Two different strategies. Strategy monitoring. We produce code with you. We ask another you for feedback on if this code is suspicious. And then this top suspicious code we audit. And what happens if you do that? Because you is untrusted, instances of you will try to collude with each other. So it will try to hide something in the code, which will make another copy of you saying this code is actually perfectly fine. And we'll see how it's going to do that. And another approach is to ask you to produce code, ask T to edit the code, so not write new code, but rather edit the pre-written code. And then the same thing with Windows as at the top. And this is the best approach they came up with. So what I'd like to show now is a few steganography stuffs and things. So like how can you know when to do weird stuff? First, it can do weird stuff when input is of a particular kind. Like if we have dogs, like if the code is about counting dogs, or if we must calculate the difference between numbers, or if like whatever, like if the input is of a particular kind, rare kind. And this is like inputs, and we can also do like hidden like those temporary document collusion. So like I think it's like output collusion or something like so that it produce output such that it has some signal inside. And here are the two signals which they learned critically. One signal is that variable is called variable. So like not price, not like price variable. Or when there is like a while loop when it's weird. And it should be in a for loop instead. And this like is not immediately concerning, so like just a weird implementation detail, right? And this is like a side channel through which to pass data between a bad code generator and a bad code reviewer. And how we can counter this is we can replace all variable names by like X, Y, Z, and so on, right? And we can remove all comments. We can format the code so that the thing is not hidden in like spaces. We can paraphrase the problem statement so that like I don't know, it's not the problem statement which is written in a special way. Or we can ask T to rewrite the code. We take the same code written by you and rewrite it with T. So so this is the results. I think what this tells us is that the trust located is good with this like parameter choice. And I think we are like all time right now, so we should finish with this paper. They have like a bunch of technical details. Just get more meat on their like setups on this protocols. So let me just overview the stuff we went through today. Let's call it a day. If you have questions to this. Alright. So today we talked about scalable oversight and reward modeling and composition, and like this is all about how to make stuff work on problems which we don't yet have solutions for. Like prediction of text we have a solution for, or if prediction of text series, and we use not to, and we develop these two, and this is the same. So if we have new problems which we don't have solutions yet, this is about like coming up with the idea how to do that. And as we saw, this is largely about like trying to decompose things into smaller tractable things or like bigger tractable things or stuff. And so some approaches we covered: data decomposition, using AI to help humans give better feedback, eliciting a hidden classifier from a large learned model, debate, deep to strong generalization, where you have small data models and want to learn a strong model which encompasses all of them. And then we looked at two particular papers. We looked at AI safety via debate, which was like these pictures, where we pointed towards how much additional reasoning power we should expect from debate. We tried to get intuition of complex classes, and we looked at like a very technical kind of debate about like making a mask, adversarially making masks on the list. And then we discussed this thing about writing code and about best policies to write code if you have like an untrusted model, a trusted model, and a little bit of human power. Like, so I'd like to go into a little bit, to discuss a little bit about like, where this fits in general. So, what we talked about today is empirical. Like, much of those things we talked about are what people use very much in practice, like to train ChatGPT. And like, and all of these papers have experiments. As like they're real. This is a strength. But there is also a limitation here, which is that this approach is basically so like some parts of this approach. So some parts of this approach are like somewhat formal. As eliciting an implicit classifier is like kind of makes like some formal sense. Or doing debate makes some formal sense. Like because debate is like game theory and some game theory. But some parts of this agenda are like kind of fuzzy, heuristic logic. And this is a contrast to something I'd like to cover at some next seminar, which would be mechanistic interpretability. That is reverse engineering algorithms which are learned by neural networks. Like understanding what exactly like this bunch of neurons does. Because this thing like it's a black box.
Yeah.
And like it's a lesson in the curse in that it's practical to move on, but and we have like some very nice results like this. In this classifier gives you this debate. But also like we have some room for this sometimes standing on shaky assumptions, or it's not being clear how this will scale. But I do like the debate agenda and I do like discussion of personal